I can agree with almost everything that Tim said. I don't agree with the NVIDIA being the future, and I don't necessarily agree with the heterogeneity, but pretty much everything else aligns very closely with what I was saying. And the point I was trying to make, he actually had some of those energy numbers that I was looking for this morning and didn't have in my slide, which say locality is critical and you can't move data around and you can't keep moving it from DRAM into memory, operating on it and putting it back out. So I don't need to introduce myself. I'm not a product guy. Well, sorry, I'm a product guy, not a sales guy. I did put some marketing slides in here, and I'll let you guess which ones they are. I'm sure you will notice them. You know who I am. I have kept slightly to the heterogeneous track here. Don't know if I was supposed to or not, but that seemed to be the theme of the day. So this is one of the places where we may disagree. Does the instruction set matter? First quote here. We find that ARM and x86 processors are simply engineering design points optimized for different levels of performance, and there's nothing fundamentally more energy efficient in one ISA class or the other. ISA seems irrelevant. This is from a paper that you can find. And another quotation here. I haven't told you who this is yet. I'm going to ask you who you think said this. I'm very happy that most of the world thinks that ARM provides a great efficiency advantage over x86. The truth is, it really doesn't. It's a small second-order effect. The reality is you squint, and there's no power advantage to ARM. Any guesses? He knows. Not ARM CEO. Tim knows. That's a slight hint. NVIDIA. CTO Steve Scott said that. So if the ISA doesn't matter for power, why bother to change it? Might as well stick with what we know works and what you're familiar with. So here's a little bit on heterogeneity. So I've been saying heterogeneity makes no sense. So now I'm asking, when does it make sense? So here is a nice picture of Haswell, which was just announced, went public 2 or 3 days ago, last week sometime. And I looked around and I searched out this die photo, which was on the Intel press site. And I downloaded it and found that it still had embargoed written across the bottom of it. So I mailed the people who run the Intel press site and said, this, and they said, oh, don't worry, it isn't embargoed. So the interesting thing about it, you can see this is an actual die photo with some annotations on it. The interesting thing is the relative areas. So this is a 4-core machine, and if you kind of do a little bit of shuffling around, you can convince yourself fairly soon that the graphics here is approximately, well, it's at least the area of 3 of the cores and possibly 4 of them. And then there's a bunch of other stuff like the cache. The cache is coherent with the graphics and all the cores. And then over here we've got all the other stuff like actually driving pins off chip and so on, and the memory control across the board. So the area on here, this is a consumer part that you know you'll find in a MacBook Air and so on. They just announced those yesterday, I think, the MacBook Airs with this kind of thing. So my conclusion from that is that it makes sense to use heterogeneity when you've already paid for the other thing, right? If you already paid for it, you should use it. So we've got all this processor graphics there that we paid for already for doing graphics. We might as well use it for compute as well if we want to. It makes no sense not to. You already paid for it. Here's the Xeon Phi, which we were talking about before. Intel, oh, I left off the bracket, sorry again. Intel Xeon Phi coprocessor. I'll just call it Xeon Phi. This is a version of, it is an x86 instruction set, pretty much binary compatible. I won't say completely binary compatible because it has wider vectors than the current x86 stuff. So the vectors on here are 64-byte wide in operation, so 8 doubles or 16 single precision operations. It has fuse multiply add, so you can do 16 fuse multiply adds on each core in every cycle. 61 cores, it's optimized for low energy. So I'm agreeing with Tim. Use the architecture that's optimized for low energy when you need to be in these high performance things. It's just that it's the implementation that's optimized for low energy. It's not the instruction set. You don't have to change your instruction set. It's cache coherent. talks to GDDR5, as we mentioned before. That's the secret source in all of these things. And it runs Linux, C, C++, Fortran, OpenMP, OpenCL. Now here, you've just got there's no graphics on here at all, right? So there's no need for any heterogeneity in that programming model. It's just got CPUs, the vector floating point units, the caches, the interconnect, the memory interfaces, and the 61 cores. So the reason to have this different thing, heterogeneous in implementation, is because it's giving you something that you can't get elsewhere. The main CPUs, as Tim said, they're optimized for main CPU type things. They have the out-of-order processors that are good at executing code that is poorly written. That's what they're there for, right? They manage to reorder the instructions on the fly and extract instruction-level parallelism from these poorly coded pieces of stuff. And they have limited memory bandwidth. Obviously, we push the bandwidth up as hard as we can, but it's an economic issue. People don't want to pay more on those CPUs for more memory bandwidth. Here, as we were discussing this morning, memory bandwidth is absolutely what you're paying for. So you do want to pay more for it, so you need the GDDR5. So it's heterogeneous in implementation because your code needs something that you can't get anywhere else, right? So it needs a different implementation. Programming models. Do you have to rip it up and start again? Anyone recognize rip it up and start again? Orange juice. Rip it up and start again. So do you have to do it? Well, we think you don't completely. I mean, I was mentioning AOS and SOA, and if your code is written with array of structures, well, maybe that's really horrible and you do have to rip it up and start again. And there's nothing that anyone's instruction set can really do about that easily. But at least we provide you with a native programming environment that's a Linux. You can SSH into this node, and you can cat proc CPU info, and you can see your 244 logical CPUs there, if you've got a big enough screen. And you can, there's a shell there, you can run stuff. Or you can offload from the host. You can do that using Intel syntax because at the time that we were doing this, OpenMP didn't have extensions for doing that. So we need to program the machine. There's nothing we can do about that. But now OpenMP 4.0 is going to be out. I mentioned this earlier, a meeting in Toronto last week that has pretty much agreed all of the specification. There are a few things still to be done, but it should be out. Well, I imagine that they're hoping to have it out at ISC. I need to check that, but it seems a logical conclusion. And that supports Target, which is a way of saying, offload this piece of computation to an accelerator of some sort. That could be a GPU, could be a Xeon Phi, could be, don't know what else. And then Teams and Distributor, another couple of, so Target does two things. One thing it does is it says, take this chunk of code, offload it. And the other thing is you can use it to annotate variables and move data backwards and forwards. So that's in standard OpenMP. There's no need to go outside standard OpenMP. It's in our beta test compilers any day now. We committed the runtime that supports that a couple of weeks ago. It's gone through testing. It'll be out really soon. We support OpenCL 1.2, and you can also use full native languages in the offload. So I can have a C++ code that does offload, that then uses threading building blocks on the target. Full C++, virtual functions, everything you would expect. It's an x86. Why wouldn't it be there? And then, of course, in the other place, the processor graphics that we saw on the Haswell, then we support OpenCL because that's the sensible way to program GPUs. So open standards are critical. They encourage portability, which is immensely important, as I was saying this morning. Codes are old. And not only are they old, but you hope that the one that you're writing today will become old, right? You hope no one's going to, that the effort you put into writing it today isn't in 2 months' time going to be thrown away because something changed and the code is no longer useful. So preserve your investments in code, portability into the future, and your brain cells. You already know how to write most of these languages. So if you can continue to do that, that is a good thing. Invest in common tools and programming models. See, look at this great build. Yeah, oh, well done. Right. So you take your code, you compile it with the compilers, and it goes one way onto the Xeon and the other way onto the Xeon Phi. Isn't that great? So use one software architecture today, scale forward tomorrow. And prompt. Well done. You can use all of these same things, Silk, TVB, OpenCL, OpenMP, offload with the compiler, MKL, math kernel library, MPI, and Fortran, all the things you would expect. And there are parallel models that support the heterogeneous environment in a portable way. Is it really that simple? Well, of course not. It's easy to port stuff, but getting performance requires tuning. At least you're doing tuning with the same kinds of tools that you already know and love or hate, but at least they're familiar. So vTune, for instance, works perfectly well with the Xeon Phi. And the other thing that really, to some extent, seems to surprise people, although I'm not entirely sure why, is that the tuning that you do for the Xeon Phi in terms of improving parallelization, improving vectorization, actually helps the CPU too. So a lot of our application engineers were given the task, they were told to take some code and please make it run, 2x faster on the Xeon Phi than it does on the CPU. Fine. They go away. They measure the two things. The Xeon Phi is not as fast as it should be. They do a load of optimizations. They double the speed on the Phi. They think, great, I'm done. Then they run the code on the CPU and it runs twice as fast. And they've made no progress to their goal because the ratio is still the same. Everything's running twice as fast as it was beforehand, but their goal that they were set by their management is not met. And they're going, this is really bad. And I'm going, this is really good. Right? You just doubled the performance on the CPU. What's not to like? So you're not wasting your time. You're not writing something in a vendor-specific language that you have to throw away if you can't get it to work. And in any case, paying a bit of attention to your old code, reading it, tuning it is worth doing. And it's not something people do. And it would be beneficial for a lot of people if we did. So we're committed to open standards, OpenCL, OpenMP. See, I did get the asterisks in there. MPI, normal programming languages, the support for the Phi is in the compilers. If you buy compilers, it's there. Familiar programming environments, Linux, Windows, support for Xeon Phi hanging off a Windows box is there in beta if you want it. And we can perform at huge scale and high energy efficiency. If we're talking about number ones, we're still number one in the Green 500, probably until next week. And we're expected to be number one in the top 500 with this funny machine in China. There you go, legal disclaimer.
Thank you very much. Thank you, Jim. Now, this time, do we have any questions from online? Not this time. Okay, good. So, well, we've got a few hands up already. Here we go.
Just a bizarre question of curiosity. Why 61 cores?
So that's a programmer's question. It's not. Think of it from the completely other end, right? I have a wafer that has a particular size. I have a reticle that can project a particular sized thing onto it. I design my core, it's a particular area. I lay it all out and I get a size. And how many can I fit, right? So it doesn't come from anything to do with the logic of wouldn't it be nice to have 64 or 65 so that you can have one for doing something else and 64 that you can use. It comes completely from what can I manufacture.
Okay, next question.
No, it isn't that.
In two other presentations today, including one from NVIDIA, there was promoted a model when you have multiple CPUs with local memory and no cache coherency. why could you maybe comment why you're going for cache coherency? Because I think there, especially if you go for 61 cores, then maintaining cache coherency between 61 cores looks like a significant overhead. And maybe if your software could be doing this, maybe you can do it smarter.
So, okay, so a number of reasons. Firstly, x86 processors are cache coherent. If we changed that, everyone would kill us, right? So you would, if you want a non-cache coherent thing, I mean, we did, if you go and look, we did a thing called the single chip cloud computer that was an Intel Labs research project that had a number of x86 cores and was not cache coherent, right? And they played around with that, and the Microsoft operating system guys in Zurich had fun porting their cloud operating system, and people have used it, and it's fun, and it's fine. But if you were doing this, you would have to take a decision as to how big the coherency domain should be, right? So suppose I've got my 61 cores. How big a coherency domain do you want? You're going to go down to 1 core, to the level of 1 core in coherence, so you're going to have 4 cores coherent and chunks of 4 cores coherent. And designers don't like taking those decisions because it's always the wrong decision for someone, right? If 4 cores is the right, if 16 threads on 4 cores is the right decision for one application, there'll be another application that says, but it would have been so much nicer if I could have had 16. So unless you have a really strong reason not to do it, then you just go, well, I'll just do it. And if you talk to the hardware guys, and there's a presentation from last year from Hot Chips last year, where there's a discussion of the cost in area of different components of the Xeon Phi. And the cost for being x86 compatible and for having the cache coherency is something like 2 or 3% of the die, right? Most of the die is either cache or a fuse multiply add units and vector registers, right? So when it's a small cost and there's a big penalty, and it's hard to justify, then making a change. Now, in the future, it may well be that as Tim was pointing out, there are benefits to going to smaller components in general, right? So for your exascale machine, it may be that having 61 cores and 244 threads in your coherency domain is too large, and you might be better with 32 cores and 256 threads or whatever it is, right? And building things that aren't reticle limited. But that's a system level design decision, right? Because the issue then becomes, when I'm building an exascale machine and I have my MPI processes, how much remnant parallelism is there inside the process after I've taken out MPI parallelism at the top and vector parallelism at the bottom, right? What's left in the middle, which is, as it were, the OpenMP parallelism. And what I get beaten up about as the OpenMP guy is always, well, I've taken out all good parallelism up here, I've taken out a vector parallelism, and now I'm trying to run these OpenMP loops that run for 500 nanoseconds, and it takes too long to fork them and join them. Well, yes.
So in the interest of time, we will leave it there, but let's thank Jim once again. Thank you very much, Jim.